Good morning, everyone. Today's lecture focuses on circular urban design fundamentals. In this session, we will discuss how cities can move from linear systems of consumption toward more circular and regenerative models. The main focus will be on flows of energy, water, and materials, and on how urban design can help reduce waste, improve efficiency, and support resilience. We will begin with the core conceptual foundations of circular urban design, then move to the main principles of circularity in urban systems, and finally look at several case studies that show how these ideas can be implemented in practice. Let us begin with the first 6 fundamentals of circular urban design. The first is systems thinking, which means understanding cities as interconnected socio-ecological technological systems rather than isolated sectors. The second is the urban metabolism perspective, which helps us see water, energy, materials, and biomass as flows that can be optimized. Third, water-energy-food nexus integration reminds us that these systems are interdependent. Fourth, circular urbanism aims at ecological regeneration, not only efficiency. Fifth, nature-based solutions are treated as real infrastructure. And sixth, circularity depends on closed-loop logic, meaning reuse, regeneration, and waste minimization. This slide visually reinforces the same 6 points. What is important here is not to read them as separate ideas, but as a connected framework. Systems thinking, ecological regeneration, and nature-based solutions all work together. In circular urban design, the city is no longer seen as a place where resources simply enter and leave. Instead, it becomes a place where flows can be restructured, supported by ecological processes, and redesigned to reduce loss and increase long-term urban performance. The second half of the fundamentals adds 4 more important ideas. The 7th is multifunctionality, meaning that urban elements should deliver ecological, social, and technical benefits at the same time. The 8th is decentralized and distributed networks, which support local loops and reduce dependence on single centralized systems. The 9th is adaptive capacity and resilience, because circular systems should be able to absorb shocks such as climate stress or supply disruption. The 10th is evidence-based monitoring, since circularity requires indicators and measurable performance in order to be effectively managed over time. This slide continues the visual presentation of those last 4 principles. Together, these ideas show that circular urban design is not only about reducing waste. It is also about creating urban systems that are more flexible, more integrated, and more capable of responding to change. Multifunctionality, decentralization, resilience, and monitoring help translate circularity from a broad vision into an urban design approach that can be assessed and improved over time. After defining the fundamentals, we now move to the principles of circularity in urban systems. While the previous slides introduced the conceptual foundation, this section focuses more directly on how circularity can guide planning and design decisions. These principles help us understand what kind of interventions are needed if we want to move from a linear model of resource use toward more regenerative and interconnected urban systems. The first 6 principles are listed here. First, we should prioritize resource efficiency before expanding supply, which means reducing demand before adding new infrastructure. Second, we should design multifunctional solutions, so that one intervention can solve several problems at once. Third, circularity requires us to close loops through reuse, recovery, and regeneration. Fourth, nature-based solutions should be integrated into all feasible urban sectors. Fifth, resource loops should be localized through decentralization. And sixth, waste streams should be used as inputs for other processes, turning wastewater, biomass, and organic waste into useful resources. This slide emphasizes those same first 6 principles in visual form. The key message here is that circularity depends on a shift in logic. Urban systems should not be organized around one-way flows and end-of-pipe disposal. Instead, they should be designed around reduced demand, repeated use, and interconnection between systems. What looks like waste in a linear model may become a valuable input in a circular one. This is one of the central changes in circular urban thinking. The second half of the principles focuses on enabling conditions. First, interventions should be designed for climate adaptation and resilience, meaning that they should contribute to flood mitigation, heat reduction, or redundancy. Second, circularity requires stakeholder engagement across sectors and communities, because no single profession can manage all urban flows alone. Third, governance, policy, and finance must be aligned to support circular solutions. And fourth, circular systems need to be monitored, evaluated, and adjusted continuously. Circularity is therefore not a one-time design act, but an ongoing process of learning and adaptation. This slide reinforces an important point: circular urban design is not only technical. Even the best design solutions will remain limited if institutions, communities, and governance systems do not support them. That is why resilience, participation, policy support, and monitoring are essential. Circularity needs collaboration, institutional continuity, and regular evaluation if it is to become part of mainstream urban practice rather than remain a small-scale experiment. This section introduces the transition from linear to circular flows. It shifts the discussion from broad principles to the actual movement of resources through the city. The question is no longer only what circularity means, but how water, energy, and materials can remain in use for longer, how waste can be reduced, and how urban systems can be redesigned to function through loops rather than one-way extraction and disposal. The first 5 key points explain the core problem and the basic alternative. First, cities still largely work in linear ways, following a take-use-waste model. Second, circular flows aim to keep resources in use for longer through reuse, recycling, and regeneration. Third, water, energy, and food systems are interconnected, which is why the WEF nexus is important. Fourth, nature-based solutions support circularity by storing water, filtering pollutants, cooling buildings, and producing biomass. And fifth, water can be captured and reused through stormwater harvesting, infiltration, and wetland-based treatment rather than simply being drained away. This slide visually continues the same argument. The key issue is that linear systems generate loss at every stage. Circular systems try to slow down those losses and convert them into useful cycles. Water is one of the clearest examples. In many conventional cities, stormwater is treated mainly as a drainage problem. In circular urban design, that same water can be retained, filtered, infiltrated, and reused in ways that support both ecological and urban performance. The next 5 key points extend this logic. Sixth, wastewater contains valuable nutrients, which means it can support fertilizer, compost, or energy production if treated appropriately. Seventh, urban green infrastructure reduces energy demand by cooling cities naturally and decreasing reliance on mechanical air conditioning. Eighth, organic waste becomes a resource when it is composted or converted into renewable energy. Ninth, multifunctional designs support several loops at once, as in the case of a green roof that manages stormwater, reduces heat, and supports biodiversity. 10th, circular systems require integrated planning across professions and sectors. This slide reminds us that circularity is most effective when systems are not planned in isolation. Water, biomass, materials, ecological processes, and urban design decisions all interact. That is why engineers, ecologists, planners, designers, and communities need to work together. Integrated planning is not just an organizational preference here. It is necessary because circular systems depend on the relationships between different flows and different forms of expertise. This diagram is very important because it shows nature-based solutions within the water-energy-food nexus. The arrows indicate exchanges between water, energy, and food nodes, while gains and losses are identified in relation to each one. The point of the slide is to demonstrate that these systems are not independent. A change in water systems affects energy and food systems. A change in food systems affects biomass, waste, and land use. And energy systems also shape the viability of water treatment and food production. Nature-based solutions help strengthen these connections in more circular ways. What is especially important in this diagram is that broader dimensions such as livelihood, circular economy, security, and planetary boundaries are overlaid on top of the resource flows. This means circular urban design is not only about technical efficiency. It is also connected to social well-being, economic models, long-term resilience, and environmental limits. The WEF nexus therefore becomes more than a technical tool. It becomes a way of seeing cities as layered systems in which ecological, social, and infrastructural processes are deeply entangled. This slide marks a transition from diagnosis to response. It suggests that moving towards circularity is not only a matter of technology, but also a matter of identifying knowledge gaps and implementation challenges. Many urban systems remain linear because planning is fragmented, sectors are disconnected, and existing knowledge is not translated effectively into integrated design strategies. Circularity requires us to recognize where the gaps are, whether they concern coordination, awareness, technical capacity, or cross-sector understanding. The broader message here is that circular flows can help ensure water, energy, food security, but only if the gaps between problem recognition and solution development are addressed. In other words, circularity depends on learning as much as on infrastructure. It depends on connecting sectors, combining different types of expertise, and moving from isolated technical responses toward system-based strategies that respond to multiple urban challenges at once. The presentation now turns to a set of best cases. These examples are important because they show that circular urban design can operate at multiple scales and in different forms. Some cases focus on floodable public landscapes, others on greywater reuse, district redevelopment, productive rooftops, or citywide policy. Together, they demonstrate that circularity is not limited to one model. It can be adapted to different urban conditions while still following the same basic logic of reuse, regeneration, multifunctionality, and integration. La Margelle Floodable Park is presented here as an iconic example of circular stormwater reuse. The project demonstrates how a single urban space can perform several functions at once: flood protection, water storage, water reuse, climate regulation, biodiversity support, and community education. This is a strong example of circular urban design because it combines infrastructure and landscape instead of separating them. Water is not treated only as a hazard to be removed, but as a resource to be retained and managed through a multifunctional public space. This image reinforces the idea that circularity can be spatial and visible. La Margelle is not hidden infrastructure. It is a public urban landscape that makes circular water management legible. That is important because circular urban design often works best when ecological and technical processes are not concealed but integrated into public space. The project shows how natural processes can support flood control while also improving urban amenity and environmental quality. The Pune Greywater Green Wall case shows that urban water can be treated as a resource rather than a waste product. It demonstrates a micro-scale circular urban water loop by integrating natural treatment systems, efficient resource use, and community engagement. The project is valuable because it proves that circularity does not only belong to large-scale infrastructure projects. Even relatively small interventions can create effective loops when water is filtered, reused, and connected to ecological systems rather than simply discharged as waste. This slide highlights the applied side of the case. The project provides a practical blueprint for circular urban design because it links water treatment, ecological function, and user awareness. It also shows that circularity often depends on rethinking ordinary urban systems. Greywater, which is usually overlooked or discarded, becomes part of a useful and visible loop. In this sense, the project is both technical and educational, demonstrating how communities can interact with circular infrastructures. The Fornebu Eco-District is a district-scale example of circular urban transformation. It shows how a post-airport site can be redeveloped through land reuse, ecological regeneration, and an adaptable urban structure. The project integrates blue-green infrastructure, energy-efficient building standards, and multimodal mobility. It is especially important because it demonstrates circularity at a larger urban scale. Here, circular urban design is not limited to one intervention, but becomes part of a broader redevelopment strategy involving land, infrastructure, mobility, and long-term planning. The image of Fornebu helps underline another key idea: circular urban design requires flexibility over time. Densification, mixed uses, and transit upgrades are not fixed outcomes but parts of an evolving urban structure. The case therefore shows that circularity is not only about closed loops in the present, it is also about building urban systems that can adapt as needs, technologies, and environmental conditions change in the future. Brooklyn Grange exemplifies circular urban design by transforming idle rooftops into productive systems. Its green roof infrastructure captures and reuses stormwater, while engineered soils support long-lasting nutrient cycles. On-site food and honey production shorten supply chains and reduce waste. This is an excellent example of how circularity can work at the building and rooftop scale. It demonstrates that even surfaces usually considered unused can become active components of urban metabolism and local resource cycling. This slide makes the productivity of the rooftop landscape more visible. What matters here is that one intervention creates several benefits at once: water management, food production, biodiversity support, and a reduction in resource waste. Brooklyn Grange therefore reflects the principle of multifunctionality very clearly. It also shows that circular urban design can emerge through retrofitting existing urban surfaces, not only through entirely new master plans or large redevelopment projects. Basel Green Roofs is presented as a case where circularity is supported through policy, incentives, and mandatory regulation. By transforming flat roofs into multifunctional ecological surfaces, the city closes loops in water management, reduces building energy demand, and enhances urban habitats. This case is especially important because it shows that circular solutions can be mainstreamed. They do not have to remain isolated pilot projects. When governance supports them, circular design strategies can become part of wider urban policy and building practice. This image helps reinforce the broader lesson of Basel. Circular urban design needs not only good projects, but also institutional support. Green roofs in this example contribute to adaptation and mitigation at the same time. They reduce heat, support biodiversity, and improve water performance. The case shows how circularity becomes more effective when ecological design is backed by policy continuity and city-scale implementation frameworks. At this point, we can briefly pause and reflect on the common thread across all of these cases. Although the projects differ in scale and context, they all show that circular urban design works by connecting systems rather than separating them. Water, ecology, energy, materials, public space, and governance are all brought into a shared framework. This is what allows circularity to move from a theoretical concept to an operational urban strategy. To conclude, circular urban design represents a fundamental shift in how we understand and shape cities. Instead of one-way systems of extraction, consumption, and disposal, it promotes regenerative loops in water, energy, materials, and biomass. The main foundations discussed today include systems thinking, urban metabolism, WEF nexus integration, ecological regeneration, nature-based solutions, multifunctionality, decentralization, resilience, and monitoring. These ideas help create urban systems that are more efficient, more adaptive, more ecologically integrated, and better prepared for long-term sustainability.